So in this lecture I introduce Monte Carlo integration. Now Monte Carlo integration is actually a very simple way to integrate, and you use simple heuristics, and we are going to make these heuristics more precise. So in Monte Carlo integration, what we are going to do is we are just going to count the number of points, and counting the number of points will actually give us the answer for integration. Now that is very simple. Now this method was used extensively in the Manhattan Project because they wanted to carry out a large number of computations as fast as possible, and for the purpose of secrecy it was called Monte Carlo integration. So Monte Carlo is the name of a French town in which there are a lot of casinos. So let us now do an example. So first we do a standard example. So say you want to compute such an integral. So this integral, you have 3x squared dx, you compute the antiderivative, and then you go the limit 0 to 1, you get 1. So this is our standard integration using fundamental theorem of calculus. Now say you want to do numerical integration. Say you do not know the fundamental theorem of calculus and you want to do a numerical integration. In that case you form limiting sums. So what you do is you draw rectangles under this curve and then you form a limiting sum. Now if you try to form a limiting sum, it requires a lot of effort. So instead of forming a limiting sum and then taking the width of the rectangles under this curve 3x square smaller and smaller, we use a much simpler method of Monte Carlo integration, which is just point counting. So let us come to this method. What is it? So this is how the graph of 3x square looks like. So this is y is equal to 3x square. So we want to find the area under the curve. So limits are 0 to 1. We want to find the area which is under this curve. So there are 4 steps to Monte Carlo integration. The first step is you need to set the target area. So our target area is what we can compute very easily. So that is 0 to 1 on the x-axis and 0 to 3 on the y-axis. So this is your target area. So your target area is, this is 1 and this is 3. So our target area is 1 times 3. So you know that your curve is lying in your target area. So then you throw n darts in the target area. So now we are going to throw some darts in the area. That is, you select points uniformly in the target area. So I'm just putting points randomly in the target area. So points could land anywhere. So then you have put a bunch of points. So now you have put n points in the target area. So n points are in the target area. Now you calculate number of points under the curve. So you just have to count the number of points under the curve. So all these points you have to count. So there are p points which are under the curve. So you compute the proportion of darts falling under the curve. So proportion of darts falling under the curve is p by n. So this is p by n. So then you multiply this proportion with the target area. So then you multiply this proportion with the target area. The target area is 1 times 3. That is the area of the rectangle. So this is the method. Now let us just give a quick justification of such a technique. So the justification for such a technique, this comes from the central limit theorem. So I've talked about the central limit theorem in my lectures on probability, but this basically says that if you put more and more points, you will get more precise estimates of 1. So 1 is the exact answer. We are going to now do Monte Carlo simulation to see what answer we get. Now this Monte Carlo simulation is very useful where closed analytic solutions of integration are not available. So it is not possible to integrate every function and get a function form like this. So it might not be possible to get an antiderivative. So therefore you have to do numerical integration, and this is much simpler than numerical integration. So let us now see the R code. So the step 1 is you set the function 3x square. This is right here. You set it here, 3x square. Then these two I have just shown for illustration. So this is just for illustration. We are not going to use this for computation. So we are going to draw the curve so that you can see the curve between the points 0 and 1 for x, and between y is also lies between 0 and 3. So the color of curve is going to be red. Then I'm going to throw a bunch of points, exactly 100 points I'm going to throw. So notice that each point here has two coordinates. It has an x coordinate and a y coordinate. So when I'm throwing points, I have to give the two coordinates. So this part is the x coordinate, this part is the y coordinate. So this is R unif. So R uniform. So this is R uniform, R unif. So x coordinate is between 0 and 1. So 100 points between 0 and 1. And y coordinates is 100 points between 0 and 3. So obviously every point has two coordinates. The x coordinate will lie between 0 and 1, and the y coordinate lies between 0 and 3. So you can see the y coordinate goes from 0 to 3, and the x coordinate goes from 0 to 1. And that's precisely what we have done here. The x coordinates goes from 0 to 1, y coordinates goes from 0 to 3, and then you have points with x and y coordinates. This is the x coordinate and this is the y coordinate. And there are 100 points, and we are taking this from uniform distribution. So throwing darts randomly means that you are taking points out from a uniform distribution, and we are going to color these points in blue. So this we will draw to see. So then we are going to forget about these two lines. So forget about these two lines. Now we are going to set this big N to 100,000. So I'm not putting 100,000 points here because otherwise it will look too cluttered in the figure. But for computation we will use 100,000 points. So you have 100,000 points. We have already set the target area as 1 times 3. Now you have to count the number of points under the curve. So how do you do it? So obviously the point on the curve, so any point on the curve, so say you pick this point on the curve, it has two coordinates. The first coordinate is the x coordinate, the second coordinate is f of x. Now say this point lies under this point. So this point, say in particular, lies under this point. So this point will lie under the curve only if the y coordinate of this point, so the y coordinate of this point is say y1, and it will also have an x coordinate. So the y coordinate here has to be less than f of x. So notice that you are measuring this part. So you are measuring this part. Lying under the curve means lying under the curve in this direction. So that would only mean that f of x is greater than y of 1. And that is precisely here. So this is f. Now you are putting in the x part, f of x. So x is between 0 and 1. And now we are drawing 100,000 points. So f of x is greater than this point under it, y1. And y1 is between 0 and 3. So this is important. So if this condition holds, that means the point is under the curve. So if this condition holds, that the point is under the curve. So this condition holds will give you true. So if the point is under the curve, this will be true. If this is true, this will be set equal to 1. And when you sum up all these true points, you will get the total points which are under the curve. So now you compute the proportion of darts. So that is number of points under the curve divided by n. Then you multiply it with the area of your rectangle or target area, which is 1 times 3. And this should give you a answer which should be close to 1. So let us run this in R and see. So let us first draw our curve. So notice we have the curve in red and we have thrown some points on it. So we have to count the number of points under the curve. So now we are going to change. We have 100,000 points now which we will throw, and let us compute number of points under the curve and then the area. So number of the points under the curve are 33541 out of 100,000. You have 33,541, and then we have computed the area as 1.00623, which is close to 1. Now every time you run this, you will get a different answer, but you will see the answer will fluctuate around 1. So now you have 1.005, then you again run this. So this will keep changing, and that's why a number of points under will keep changing. But again, these are very close to, the answer is still close to 1. Now you have 0.99 and so on.